Now we're going to talk about how to determine the power in a multi-frequency circuit. So let's say that we have a particular circuit element of interest, and there is some voltage drop over that circuit element that is composed of a frequency term at omega 1 and another term at omega 2, much like we saw in our example problem where we found the current in through a particular element in a multi-frequency circuit. And we have some current I of t that has some bit corresponding with omega 1 and then another term corresponding with omega 2. Well, as far as the instantaneous power goes, we know that by definition, the instantaneous power, Pt, is I of t times V of t, which means we're going to have to multiply these terms together. And so we are going to have, effectively it's going to be like a FOIL method like you would do in your high school algebra class, where we're going to multiply this term by this term, then this term by this term, this term by this term, and then this term by this term. And if you have more than two frequencies, it gets just uglier and uglier and uglier. But there is a little bit of method to the madness. Another thing that we're going to be utilizing is this trig identity, cosine angle 1, cosine angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. And we will very likely wind up using this trig identity, cosine of negative an angle is equal to cosine of positive the angle. I know if we were actually using numbers, we would for sure wind up using this guy, but we may not actually have to use it in this symbolic derivation. All right, so applying that first trig identity, we can see that we are going to have 1/2 Vm1 Im1 cosine. And so we're going to take this angle and subtract this angle from it. So omega 1t plus theta v1 minus omega 1t plus theta I1 gives us theta v1 minus theta I1 plus 1/2 Vm1 Im1 cosine twice omega 1t plus theta v1 plus theta I1. That's our first term. Now we're going to be multiplying this bit by this bit, so that's going to give us 1/2 Vm1 Im2 cosine. So we have this angle minus this angle. So that's going to be omega 1 minus omega 2 t plus theta v1 minus theta I2 plus 1/2 Vm1 Im1 cosine omega 1 plus omega 2 t plus theta v1 minus, plus theta I2. So notice in our example, we have two distinct frequencies, omega 1 and omega 2. And we're only halfway done foiling this stuff out, and we have a DC term, a twice omega 1 term, a difference of omega 1 and omega 2 term, and a sum of omega 1 and omega 2 term. So our voltages and currents are operating at two frequencies, and thus far our power has four distinct frequencies that it's oscillating at. This is why this instantaneous power stuff gets real weird and real cumbersome very, very quickly. All right, so now we're going to multiplying this VM2 term by both of these currents. So we're going to get 1/2 VM2 IM1 cosine omega 2 minus omega 1 t plus theta V2 minus theta I1 plus 1/2 VM2 IM2 cosine omega 2 plus omega 1 t plus theta V2 plus theta I2. Now, before we move on from here, we should note that this guy, omega 2 plus omega 1, is operating at the same frequency as this guy. So in theory, we could combine these two together. It would be much easier to do if we had numbers put in. We could see that this was, let's say 10 cosine 20t plus some number of degrees, and this would be 15 cosine 20t plus some other number of degrees. We know how to add those two functions together, but symbolically it's going to be very difficult. Another thing here, omega 1 minus omega 2 is going to be negative omega 2 minus omega 1, which is where this trig identity would come in. So these two terms could be combined as well. And then lastly, we are going to have, let's see, VM2, so 1/2 VM2 IM2 cosine. So now it's this guy, omega 2 plus theta V2 minus this guy, omega 2 plus theta I2. That's just going to be theta V2 minus theta I2. So that is another DC term. And plus 1/2 VM2 IM2 cosine twice omega 2 plus theta V2 plus theta I2. So we wind up getting 5 distinct frequencies in our solution here, right? So we have a DC frequency, a twice omega 1 frequency, a twice omega 2 frequency, the difference of the two frequencies, and the sum of the two frequencies. That's 5 distinct frequencies at which our power is going to oscillate when we have a two-frequency, multi-frequency circuit. So if we had this oscillating at 3 different frequencies, we could just imagine how ugly this math is going to get. Now, this is the instantaneous power, and again, if we were using numbers, we could see that these guys can combine, these guys could combine. But let's talk about the average power. All right. The average power we found in our discussion of instantaneous power and average power that it was simply the DC portion of the instantaneous power. So in this case, we could see that P average is simply 1/2 VM1 IM1 cosine theta V1 minus theta I1 plus 1/2 VM2 IM2 cosine theta V2 minus theta I2. Nothing really wild there. What I find particularly interesting about this result, though, is that this is the exact same result that you would get if you mistakenly tried to apply the superposition theorem to a power relationship. And so by that I mean, let's see how I can explain this without being ludicrously confusing. We're taking this frequency term, this omega-1 frequency term, and this omega-1 frequency term, multiplying them together and getting the average power from that. We're taking this omega-2 frequency term and this omega frequency 2 term, getting the average power from that, and then adding those two bits together gives us the average power. Superposition theorem is only supposed to work for linear quantities, and power is inherently nonlinear because it requires us having the product of two functions. But the average power gets around that because when we take the average value of all of these non-zero frequency terms, so if omega doesn't equal to 0, the average value of all of these sinusoids is going to go away because half the time it's going to be above the horizontal axis and half the time it's going to be below. So we actually have a very neat and nice closed form solution for the average power in our multi-frequency circuits that can be just taken by using the average power relationship for each individual frequency and then adding them together. All right, thank you guys for watching.